This physics video is presented to you by the 4 majors. My name is Sir Edgar Angeles. But before anything else, please click the subscribe button and hit the notification bell to get updated when we upload new videos like this. Now let's get into it and explore the conservation of energy. The law of conservation of energy states that energy is not created nor destroyed. It can only be transformed or converted from one form into the other. We mean to say that all types of energy obeys the conservation or the law of conservation of energy. For us to make sure that energy is conserved in a system, we must not allow it to escape from the system. So in thermodynamics, we have 3 types of systems, namely the open system, the closed system, and the isolated system. In an open system, both heat and matter is allowed to enter and exit the system. So in this case, if we're going to count and to measure the energy changes, it will not be constant. So you cannot be sure that energy is conserved. In an isolated system, however, so in this system, it has an infinitely rigid boundary, and we are sure that energy cannot escape nor matter. So we are going to talk of the ideal system, which theoretically exists, and it's called the ideal system. It is a well-defined space whose boundary does not allow escape of mass and energy. Now that we have something to separate the system from the environment, so we have to determine the forms of energy that we are talking to. So we have two forms of energy. We have the potential energy. This is the type of energy that can be stored for later use. And we have the kinetic energy, which is the energy gained by matter or by objects by the virtue of its motion. Under the potential energy, we have the gravitational potential energy, and I'm gonna put the link on the description below about the video that we have made for gravitational potential energy. Alright, so we have the elastic potential energy, which will be the topic of this video. Later on, I'm gonna be discussing the elastic potential energy. So this energy is derived from the deformation of elastic objects. Alright, so we have the chemical potential energy. This energy is released when chemical reactions happen, and it involves the creating and breaking of chemical bonds. We also have the electrical potential energy. This type of potential energy governs electrical charges, and we will be making several videos for this. Alright, we have the nuclear potential energy. So nuclear potential energy comes from the heart of the matter. It will be released upon nuclear fission and nuclear fusion. Moving on, we have some form for kinetic energy. We have the thermal energy, which is derived from the movement of molecules of matter. So it has 3 types of motion: the rotational, the translational, and the vibrational motion. So all of this motion something to do with the thermal energy of matter. We have the light energy that travels through empty space. We have sound energy that travels through a medium, alright, which is air or solid objects. So it cannot travel in an empty space. And we have the mechanical energy. We have electrical energy, and we have the magnetic energy. So magnetic energy is due to the spin of the electrons. Alright, so if it's spinning into one direction, it creates a magnetic field or magnetic energy, if you call that. Alright, so you can create a permanent magnet if you orient the spin of the electrons into one direction. So the most efficient way of converting one form to another is seen in nature. So we are going to study how nature is conserving and converting one form of energy into the other. So we have the energy cycle that existed long before our existence. So we have the sun as the center of our solar system, right? And it gives off radiant energy, and that is picked up and used by the plants to create food, alright? And those food are eaten by the herbivore type of dinosaur, and they become a prey to this predator, which is the T-Rex or some other predators that eat meat. Alright, so when they died, they are buried down to the depths of the earth, and they became fossil fuel. Alright, so the chemical energy is stored in these rocks, and we derived it. So and we use it to power our cars nowadays. But long before the existence of these dinosaurs, way back 4.5 billion years ago, we have a superhero called Spirulina. So Spirulina has a large role in changing the complexion of the atmosphere. Alright, so because the primitive atmosphere does not support life because it doesn't contain much oxygen. Alright, so and not only that, according to studies, Spirulina has a lot of health benefits. If you want your own Spirulina, to take your own Spirulina, I'm going to put the link and the discount card below, so that when you buy your own Spirulina, you will be able to have discounts. So we create our own ways on how to convert one form of energy to another. So man invented machines that converts energy. So we have motors, just like what you can see. We have the AC motor, we have the DC motor. Both of these converts electrical energy into mechanical energy. Alright, so what else? We still have an engine, which is commonly seen in cars, alright, in ships, alright. So this is powered by petroleum products, gasoline and diesel. Alright, so it powers your car. So we still need something to fly, so man invented, alright, so turbines, so jet engines. Alright, so just what you can see. Okay, so it also converts energy, chemical energy, into mechanical energy that enables you to fly. We still have developed, or we developed something for harnessing nuclear potential energy, and we have a nuclear facility or nuclear power plant over here. So in this diagram you can see that we have a core, alright. So right here we're in the splitting of the uranium atoms into almost similar nuclei is being made possible. So we have the reactor over here, and when the reactor splits the uranium, it releases tremendous amount of energy according to Einstein's formula, E equals mc squared, and that heats up water, and that turns water into steam, and that steam drives the turbine over here. So the nuclear potential energy first became heat energy, and then it's being converted into mechanical energy by this turbine, and that mechanical energy in turn drives the generator, alright, that converts mechanical energy into electrical energy, alright. So electrical energy is being stepped up to several million volts using the principles of electromagnetism, using the transformer, and that flows to the pylons, alright, and then before reaching our houses. So there's a lot of process that's going on in this particular scenario, and in one video I hope that we can make a clear explanation about this. We mentioned earlier that the law of conservation of energy is obeyed by all forms of energy, and right now we are going to prove it that the chemical energy follows the law of conservation of energy. So the law of conservation of chemical energy is stated that we can only extract or harness chemical energy coming from chemicals through chemical reactions. This process involves breaking and making of chemical bonds. It means that chemical transforms from one form to another, just like the reaction of fuel to oxygen that produces heat and water as its byproducts. So that law states that it's been stated by the law of conservation of mass, stating that the amount of the reactants must be equal to the mass of the products. So regardless of the form of the reactants that are produced, the law of conservation of mass must hold. Like for example, the reaction of hydrogen and oxygen that produces water. Alright, so we have the reactants of hydrogen and oxygen, and it will produce water. So we are going to balance the equation. Alright, so we are going to study that in stoichiometry, and we're going to make separate videos for that. Furthermore, we can express the law of conservation of mass and energy in a chemical reaction using mathematics. Alright, by reminding ourselves that conservation of mass in a chemical reaction states that the mass of the reactants before the chemical reaction is equal to the mass of the products after the chemical reaction. So the mathematical equation is mass of the reactants is equivalent to the mass of the products, that is, before and after the reaction. So in some cases wherein reactions go spontaneously, that means there's no need for external sources, and you do not have to input more energy to the system for the reactants to react. Alright, conservation of energy is followed. Alright, so conservation of energy is in a chemical reaction states that energy is not created nor destroyed, but can only be converted into one form or another. This means that the energy of the process or of the system before and after the process must be equal. Alright, so what I mentioned right here is this one is very difficult to prove, right? So because the system is not perfectly isolated. Yes, so that's how important an isolated system is. Alright, so moving on. Chemicals react to oxygen, they burn. Alright, so they produce heat. Conservation of heat energy. So in an internal combustion engine, just like this, we will see that the reaction of oxygen to the fuel mixture, so when ignited, expands the gas through the explosion, so energy is being released, and the expansion of gases pushes the pistons, and they make rotational motion that powers our cars. So heat energy is converted into work, but we cannot say that all of the energy is converted into functional work. Heat energy is conserved if and only if we were able to extract or convert 100% of it into functional work. So a lot of energy escapes out of the system because of design inefficiency. Alright, so such a thermodynamic system is not feasible. So such an engine is not feasible as of the very moment. We can only get high efficiency, but not 100% efficiency. So whoever solved this thermodynamic problem will win the Nobel Prize for thermodynamics. Alright, so I hope someone from you guys will be able to do this. And if you are curious enough about kinetic energy, you may want to derive a formula for it. So we remind ourselves of the basic definition of energy, which is the ability to do work. So work is equivalent to force times distance, or to be exact, displacement. So force times displacement. And we have the formula work is equivalent to W is equivalent to force times displacement, and we can rewrite it using Newton's second law of motion, which is force is equivalent to ma, and then we have to multiply it by d. Alright, but right now we have dx, and dx here is the infinitesimal change in the displacement of the object while in motion. Alright, so we can do a little bit of integral calculus, and we have to sum all the work done in the infinitesimal change dx. So we have to carry out the integration process. The formula can be written as, alright, W, which stands for work, is equivalent to force times displacement, is equivalent to this one, which is the statement of work energy theorem using the second law of motion, max dx, and we can use the integral form of m. So the integrand of this one, ax dx, from vi to vf. So it looks like this because acceleration is variable, alright, if not constant, so that will become variable, and dx is also a variable that changes as we move the object. Alright, so the total work done depends on these two factors, and we have to rewrite acceleration in some terms or in some factors that will enable us to integrate it. Alright, so what we're gonna do right now is, alright, so we treat this one with, we use the chain rule to find the right factors, alright, to make the integration possible. Alright, we can write acceleration as this one, vx dvx over dx times dx. So this is the change in the velocity with respect to the x-axis. Okay, so this one is derived based from the chain rule. Okay, now we can rewrite W is equivalent to max dx is equivalent to m, and we have the integrand from x sub 1 to x sub 2, which is the respective position of the object. Alright, so m is outside the integrand because it is a constant, and we can replace ax by this term, and we can carry out the integration. So we will integrate from the initial velocity to the final velocity. So work is equivalent to kinetic energy. Alright, so this is the integrand, and once we integrate, we start from here. So v, the exponent of that is 1, and then we add 1, so it will become v squared over here, and we will divide it by the exponent, so 1 plus 1, or by the new exponent, which is 2. So we have 1/2 mv squared. Alright, so if you are not convinced with that derivation, we can do the algebraic way of deriving this. Alright, so yeah, so we have the ke total, so we have that. Alright, so this is the final velocity minus 1/2 mvi, wherein vi is the initial velocity. Alright, so we can do we can go to the algebraic way of deriving this. Okay, so we use the major formula. Work is equals to force times displacement, which is written using the second law of motion, ma times d. Right, so we will find a factor for a and d, which can be derived from this one. So it relates initial and final velocity to the acceleration and displacement. So we will derive for AD, and it will require us to transpose BI to the other side and then divide it by 2. It will give us AD is equivalent to BF squared minus VI squared all over 2. And then we are going to multiply it by M, thereby giving us work, or W is equivalent to KA total is equivalent to force times T, or displacement is equivalent to MA times D. So we have M times BF squared minus VI squared all over 2. When you distribute this, it will become 1/2 MV squared. So there we go. We have derived the formula for kinetic energy. Since our topic is the conservation of energy, you may want to derive a formula for it. So we have the kinetic energy plus potential energy of the system or of the object must be equal to the total energy, and it will be constant. So nothing is added to it on or before or after the process. Alright, so that will remain that must remain constant. Alright, so we are going to substitute the formula that we have studied for KE, which is 1/2 mv squared. Alright, so for PE, which is mgh, and that will be equal to the total energy, and that will be constant. So we have to study one more type of energy, which is the elastic potential energy. So every one of us see or we're able to experience what the spring is, and we can compress it or we can stretch it. As a result, elastic potential energy is stored, and this is done by applying force to deform the elastic object, and we have a formula for that. So the force that we need to deform the object is given by the Hooke's law, alright, whose graph is shown right here. So the formula is F is equivalent to negative kx, wherein k is the spring constant, and it will be negative because the force opposes the direction of motion. Alright, so going back, let me just put it back. Alright, so if we want to determine the amount of energy that is used to do work on the particular system, we may use integral calculus again. Alright, so let me just put a straight line over here. Alright, so starting from this point, after that point, you will see that when you draw a perpendicular line from this point to this point, you will see that you create a triangle. Alright, so this triangle has its area, and we want this area if we want to find all the energy that was used in order to move the spring at a certain distance. Alright, so moving forward, alright, so the area under the line is the amount of work done, or is equal to the amount of work done on the spring, and we can compute this area using integral calculus again. Alright, so we can rewrite the equation as, alright, so negative k. Alright, so the integrand of x dx from a to b. So a to b is the points or distinct points, initial and final points wherein the spring is being stretched. So when you carry out the integration, it will become negative 1/2 kx squared. Now, alright, now to make this positive, we will invert the integrand. Alright, so here we integrate from a to b, next time we integrate from b to a. So this is a mathematical trick for that, and you will learn this in your calculus course. Alright, so let us check if the law of conservation of energy applies to elastic potential energy. Alright, so now we are going to study conservation of elastic potential energy. So the equation must follow or must hold that KE plus P is equivalent to the total energy of the system, and that will be constant. And this is otherwise known as the work energy theorem. So we are going to apply KE plus PE is equivalent to the total energy, and that must be constant. We have a formula for KE, right, which is the elastic potential energy, and we have the KE, which is the kinetic elastic. Alright, so we add them to we add these two, and then we are going to get the total energy. All right, and we can rewrite it like this. So we have the elastic potential part, which is given by 1/2 kx squared, and we have the formula for this one, which is the ke. All right, so we have 1/2 me squared, and we still have a problem because if we suspend a mass, all right, on the end of the spring, it will follow simple harmonic motion. And if you can recall, or if you have watched my video, you will not get any problem in deriving this. But if you haven't been visited my video about that, please visit it so that you will be able to learn how we derive the formula for the simple harmonic motion. Alright, so the motion of the block on the spring is in simple harmonic motion, and we can get its position using the formula x of t. Alright, is given by a, which is the amplitude, cosine the angular velocity plus phase angle. Alright, so this is for x. And how about for velocity? The velocity is given by the first derivative of this. So we have negative a for amplitude, angular velocity, sine, and then we get the function of this, which is the function of the angle. So using this equation and trigonometric identity, cos squared theta plus sine squared theta is equivalent to 1, and we put in mind that the angular velocity is equivalent to square root of k over m. We can substitute these equations to find the total energy of an object in a simple harmonic motion. Alright, so we plug it in. Alright, we have to follow the formula. Ke total is equivalent to 1/2 kx squared, which is, this one is the PE, and this one is the KE. Alright, and we substitute the value of x, which is a cosine the function of the angle, alright, which is the angular velocity times time plus the phase angle, and then square that. And then we substitute the formula for the velocity, which is this one. It's negative a w, which is the angular velocity omega times sine, and then the function of the angle, and then square that. So if we square terms, and we will get 1/2 ka squared plus squared, and then this function, which is the function of the angle, plus. Alright, so we have ma, or mass, times the amplitude squared times the angular velocity squared, and sine squared. Alright, so now pay attention to the angular velocity, because we can see that it is depends on the spring constant and mass, so we can substitute that there. Alright, so angular velocity is equivalent to square root of k over m, then squared, we have k over m. You will see that we can actually cancel this out. Alright, and yeah, we can rewrite it like this. So you will see that this term is common to both sides, both equations, or both terms. Alright, so we can factor this out. So we have 1/2 ka squared times cos squared plus sine squared, and then this one will be reduced to theta. So using the trigonometric identity, this will become 1. So we have 1/2 ka squared. So the energy of a simple harmonic motion, or of a spring in a simple harmonic motion, largely depends on the amplitude of the simple harmonic motion. And by that, we concluded that elastic potential energy follows the law of conservation of energy. And that's our topic for today. I hope that you will always subscribe and click the notification bell to get updated to our newly uploaded videos. Once again, this is the 4 majors, and my name is Sir Edgar Angeles. And till next time in our physics